This conference will now be recorded.
Hello, whether it's audible to students. Good morning, everyone.
Good morning, sir.
Yes, very good morning. Right, today we are here to see PD demo, right? PD advanced demo. Right? So today we'll see three agendas, right? What we do in right physical design, right? So before that, what we do in physical design, we have why physical design, why physical design, right? So next is what we do in physical design. What are the steps, right? See, you people are here for PD demo, right? Everyone. Everyone has for PD demo, right? Everyone has joined for PD demo, correct?
Hello?
Yes, sir.
Yeah. Is
Yes, yes,
it
tell me.
PD class? Because someone has shared this link for DFT.
Yes, there is some small confusion. Even I'm getting the messages. But students, PD students have got the same link, right?
Yes, sir.
Yes, sir.
Yes, it is physical design class.
Okay, maybe I can exit.
Yes, yes, sure.
Okay.
Right. So see, already you people have studied physical design. Right? You've already done. People have studied physical design. Sorry, not physical design, basics of physical design. Few have already studied that. And few already know TCL Unix. So next is why physical design. Right? What we do in advanced physical design. Advanced physical design. Next is how course, right? See, that is I can tell course timings. How the course is proceeded for entire 3 months or 3.5 months. Right? That we will see now. That is what we will see in the advanced physical design demo. So now, before going to the physical design, why physical design? Before going to this concept, so I want to discuss on two things. One is right chip fabrication. Chip. Right? One is chip fabrication. Another is chip design. So, is there any difference between these two things? Can anyone tell me? Is there any difference between chip fabrication and chip design?
Designing is
Hmm.
where we get the layout. In fabrication, we get the exact chip out.
Yes, here chip is fabricated. Chip is fabricated means here chip fabrication happens in foundry. Right? Ultimately, chip fabrication happens from foundry. So foundry is a place where chip is fabricated, and here more than right electronics engineers, you should be also having concepts or you should also understand chemical properties. Right? You should be knowing different fabrication steps, and here you should be knowing chemical properties of the substances. So I can tell more than a electronics engineer, right? A chemical engineer is required here. Chemistry should be known properly. How to do oxidization, right? How to do etching by using any acids, right? So that this place is called as foundry. So in this foundry only chip is fabricated, right? And this place, whatever I call foundry, right? The chip is fabricated. It is very clean, neat, very clean, neat. Even a small chalk dust, small chalk powder of dust, right? It will cover hundreds of transistors. It should be very clean, very neat. It should be clean and neater, like thousands times of your ICU, right? So here the IC is fabricated, but chip design involves designing a chip by using EDA tool. EDA stands for Electronic Design Automation Tool. So in your UG classes, you would have used the Xilinx, like Spice, Spice tool, or some other custom designer tools like Virtuoso, LEDit, gedit, right? So all these are EDA tools. Means we use software to design a chip. Electronic Design Automation Tool. Software we use, and that's by using this softwares, right? We will design a chip, right? That is called as chip design. So after designing a chip, so we engineers, right? Here electronics engineers are required. Here only electronics engineers are required. Electronics engineers are required. So we are in chip design, right? We are not in chip fabrication. We are in chip design. After designing a chip, right? What file we have to give to the foundry so the foundry can fabricate our chip or our design, right? See, after designing a chip in EDA tool, means in the computer, by using computer softwares, we'll design a chip. Right? After designing, what information we have to give to the foundry so the foundry can fabricate it. What information we have to give? Yes, can anyone tell me what information? See, we are designing a chip. What information we have to give to the foundry to fabricate it?
Which technology, details.
That is okay. So whether, see, for example, I have a chip design, right? The design can be described in three methods. One is you can use Verilog or VHDL. This is one form. Another one is like netlist, means gate and its connection, right? Gate and its connection. Next is layout and its connection, right? Another form of see, this is one type of design. Design can be described using Verilog or VHDL. A same design can be described by using gates and its connection, right? Gate and its connection. And third type of design is like layout and its connection. Layout of a gate, layout and its connection, right? So which one do you think out of these three things a foundry can understand? Which one you have to give? You can describe a
Layout or
circuit even
Layout.
by using Verilog. You can describe a circuit by writing the gate level, gate level connections like this, like AND gate, right? This AND gate is connecting to OR gate. Like that, even you can write the gate level connections. Even this is also possible. All right. So, what do you think? And layout, you know what is layout, right? Layout is nothing but an internal top view of a cell, right? It's called as layout. Top view, when cell is fabricated, right? When you see from the top, that view we call it as layout. So what foundry can understand? Verilog gate and layout, which the foundry can understand, do you think? Yes, Avinash has told layout in the chat box. Others, can you tell me which foundry can understand?
Layout, sir.
Yes, good, right? So layout is easily understandable by, not easily, fabrication team or foundry can understand only your layout. Fabrication, for the fabrication team, if you give gate and its connection and Verilog, they cannot do anything. So for the fabrication team, you have to give the layout and its connection, right? That is what you have to give. So based on this information, layout and its connection, the fabrication team will fabricate the chip, right? What layers to be present in your chip, what layer should not be present, everything, right? You have to give in a file called as GDS2 file. This GDS2 file has nothing like, it has only layout and its connection of a cells. For each and every gate, you can write the layout. I think you people have already studied in CMOS basics. If you know CMOS basics, you know how to draw the layout for each and every cell. And layout and its connections, if you do right, that layout and its connection, you will write into a file called as GDS2 file. There is a file called as GDS2 file, right? GDS2 file. This file you will give to the foundry so that your foundry can understand the layout and its connection. According to that, they will fabricate the chip, right? So what is meaning of GDS2? Graphical data stream information, right? Interchange, right? This information your foundry can understand. It is a layout. I think you people know what is layout, right? So what layout consists of? Can anyone tell me? You already studied. What is layout? This is a prerequisite for advanced classes. You should be knowing what is layout. So if you have an inverter like this, right? This is Vin, this is Vout, right? This is PMOS, this is NMOS, right? So this black screen is, okay, this is your layout. I want to draw the layout. So if I want to draw the layout, what are the things required? This is your layout. In this, I have to draw the layout. What is things required for the layout? First, this PMOS is fabricated in NVL, right? First one, NVL is required. This PMOS is fabricated in NVL. This yellow color is NVL. So everyone know about layout, right? If you don't know layout, there is a prerequisite that is required. So for advanced PD, this is a prerequisite, right? You should be knowing about layout. So NVL is required, and you have P plus diffusion, right? Everyone knows about this, right? You have P plus diffusion, and you have N plus diffusion, also N plus diffusion. So in between you have polysilicon, this polysilicon. This red color is polysilicon, right? This is your P plus region, and this is your N plus region. And here you have VDD. Here you have VDD rail. Here you have VSS rail. This is VSS. This is VDD. You can see here PMOS, right? This PMOS, this is source, this is a drain. Because in PMOS, source is always at higher potential. In NMOS, right? Always ground is at lower potential, right? Drain is at higher potential in NMOS. NMOS drain is at a higher potential. In PMOS, source is at higher potential. This is gate. Right. So this side I'll call it as source of PMOS. This is source of NMOS. This is drain of NMOS. This is drain of PMOS. Right. So when we connect like this, so this source, right? You see this source of PMOS is connecting to VDD. So I'm connecting this source to VDD. This connection I'm making. Here there is a contact cut. Contact cut means it is connecting your diffusion, right, to the metal layer. This VDD is metal layer. So metal layer I'm connecting to right this one diffusion. So here there is a contact cut. So here also, right, this side if you see, this is also connecting here. The source of NMOS is also connecting to VSS ground. That connection I have to make. This connection I have to make. Again, this is metal layer, and this metal layer will connect to the source, right? So here there is a contact cut. Contact cut means it is connecting from metal to right your diffusion. It's connecting, and here you can see drain and drain is shorted. I can short a drain and drain here. Here drain and drain is shorted, and I can have contact cut here. I can have contact cut here. And this metal layer, we are taking the output. Here we're taking the output. This is V out, and here I have to again connect to find V in. Right here again make a connection to find V in. This is your V in. All right, this is your V out, and this is polysilicon. Right? This is metal layer. Blue color is metal layer. So this is contact cut. So this is called as right layout. I've done the layout for inverter. So only this layout information a foundry can understand. This is one gate, right? This one gate is called as what? Inverter. This is inverter. So for inverter, you have the transistor level schematic. You have layout also. This is gate symbol, right? Your foundry can understand this one only. Right? This layout information your foundry can understand. Apart from this, your foundry can't understand anything. Now, this information is required for the foundry to understand the things. Right? So now this is our role. Role of PD is to understand PD. We have to see what is ASIC design flow. Right? So IC is fabricated by using ASIC design flow. We will see some of the aspect why we use ASIC design flow. Already you have seen, and to understand why PD, right? This question, why PD and what we do in PD. Right? Then you have to see ASIC design flow. What is ASIC design flow? ASIC stands for what is ASIC? Full form of ASIC. Now, before starting to ASIC design flow, I want to tell one thing. After designing an IC, right, design engineers will forward GDS2 file for foundry to fabricate. We have to send GDS2 file. That is our role. Right? So this GDS2 file has what? For every cell we have layout. For every cell we have layout and its connection. For example, if I want to connect from one cell to another cell, I'll take a metal layer and I'll connect to another cell. Output of this, I'll connect to input of next cell. So I have gates and its connection in the form of layout. Right? This is called as GDS2 file. So GDS2 file has layout information. So the next question is whether we will draw the layout or not. To understand that, he will go with ASIC design flow. You'll understand what is ASIC design flow. Right? ASIC design flow starts with specification. Right. So as you people already know, specification means right. We will take different specifications from the client. Right. How he wants the chip. For example, I am designing a mobile phone chip. Right. What are the specification? So what are all the functional blocks required? I should use a transmitter, right? Receiver. So camera decoding and encoding module. That is image decoding and encoding. Right. Inside I should be having GPS module, Ethernet module, Bluetooth module. Like that, what are all the functional blocks required, right? In a chip, first we have to just discuss the functional blocks required. Next, after deciding what are the functional blocks required, we have to discuss about some other aspect of chip, like what is the area, how much area the chip should have, what is the power consumption, how much power will consumption. Right. So next is what should be the power consumption. So next is like what is the operating frequency, estimated operating frequency. With what frequency your chip should operate. How many clocks we have to use, right? Number of clocks. All these things we will decide in ASIC design, sorry, in the specification step. Right? Specification is nothing but what your chip wants, how your chip should be. That is called a specification. See, after specification, we have design entry. Can anyone tell me what is a design entry? So in design entry, we use Verilog or VHDL to describe the design. Right? So why we use Verilog or VHDL? Can anyone tell me why we use Verilog or VHDL to describe the design? Can anyone tell me about this? Why?
Hello.
Yes, tell me.
Uh, because it is hardware description language.
Yes, that is what my question is. Why we have to use hardware description language?
Behavioral
For example,
purpose, sir.
I will give you an example. What is my question is like, for example, you have a mux, right? Everyone understand my question. You have a mux.
Behavioral purpose, sir.
Yes, good, right? See, for example, I have a mux. See, mux I know, right? It is a connection of gates, right? It is a mux. What is mux? This is a mux. And for example, for simplicity, you take 2:1 mux. Right? I have I naught and I1, and I have one select line, and I have output y. If select line is 0, right? If select line is 0, y is going to take I naught. Right? If select line is 1, right? Y is going to take I1. Right? This is the behavior of a mux. Why you have to write programming language like this, right? Why you have to use language like this? If s is equal to 0, right? Y is equal to I naught. Else y is equal to I1. Why I want to use programming language like this? Instead of describing like this, I can directly write it internal structure, right? Like AND gate, you use another AND gate use, like OR gate use. Right? Why I can write internal structure instead of writing internal structure? Why I have to use programming language like this? The reason for this is, right, why we use programming language to describe circuit directly instead of going to the this one, right? So the reason is, see, describing anything to its behavior is easy. See, if I ask the question, tell me the internal structure of mux, right? Hardly few will tell. But if I tell behavior of mux, right, this is truth table. Everyone can tell almost, right? But remembering the behavior of circuit is easy. But remembering the internal structure is difficult. So directly going to the internal structure is difficult. But remembering the behavior is easy. You see, for that reason only, in our VG classes, right, everyone will ask us to write the truth table for everything. Truth table is nothing but behavioral table, right? How the circuits behave. We will write, type one box like this. What are all the inputs? What are all the outputs? For everything, we write a truth table. So by using this truth table and by using this if statements or case statements, right, by using if statement and case statements, we can easily describe the behavior of a circuit, how the circuit is behaving. So see, that is easy, right? For example, so we have a ATM machine. I want to write a vanilla code for this ATM machine. See, what are all the circuits inside the ATM machine, as it's very difficult to model. But I can model easily by using this finite state machines, like your behavioral modeling. State one, right? Initial state. Right? State one is initial state. State two, right? So initial state, from initial state to initial state, we'll move to state two when card is inserted. Right? If card is inserted, if the card is inserted, move to state two. If card is not inserted, right, no card inserted, be in the state one only. So if card is inserted, after that the user is not doing any operation. He is ideal. He's not doing anything. He's not entering the pin. Nothing he is doing. All right. Come back to state one again. All right. No operation. NOPL, right? No operation. If no operation is done, come back to the initial state again. If in S2, what the state has to do means S2, what state has to do? It will ask for pin. Ask for pin. This the state has to do. Right. If pin is entered, right? If pin correct, go for next state. Right. State 3 means for correct pin. Right. After asking the pin, if he is not right, after asking the pin, right, if you, in the state 2, if you ask a pin and he is not doing anything, again go back to the initial state. That is what I have written. Right. Here again, this is also no operation. In the S2, you ask for pin, but he's not doing anything. Again, go back to the previous state. So next, in S3, you ask for amount. How much amount? How much amount you want? If he is doing anything, no issues. If he is not doing anything, he is not entering the amount for more than 2 minutes, again go back to initial state. Reset everything, right? Go back to initial state. No operation. And give his card, right? If he is entering for the money, right? How much money he want, then go to the next state. This state is cash dispatch state. Cash dispatch. So you're going to the next state if the money is entered, right? Money entered. And after cash dispatching, again go back to the initial state. So like that, you can describe the behavior of the circuit first. I just gave an example, which you know, day-to-day operation, you know. So first I can write the operation like this. I can write the finite state. If I have a complex circuit, right? First write the finite state machine like this. And now for each and every finite state, right, start describing its behavior. If I get this input, what I have to do? If I'm not getting the input, what I have to do? Start describing the circuit by using Verilog or VHDL. This is very easy. For that reason, what we do is we take a help of programming language like Verilog or VHDL to describe our complex circuit. So we are describing a behavior of a circuit, not internal structure. So why we want to use Verilog or VHDL is Verilog or VHDL will allow us to describe a behavior of a circuit, how circuit is behaving. For that reason, we use Verilog or VHDL. Right? So mainly here we use behavioral modeling. Behavioral modeling means describing the behavior by using if statements or case statements. That is called as behavioral modeling. Right? Mainly we use behavioral modeling to describe circuit. This is called as design entry. So next is right design verification. Next we have design verification. So what is design verification? So what do you mean by design verification or functional verification? It's also called as, right? Functional verification. What is this functional verification? Can anyone tell me?
Test benches preparation.
Yes, sir, right. You are going to form the test benches because the design you have written, right? This design what you have written, whether it is right doing the proper operation or not, or this design is having proper functionality or not, what we are intended for, right? We have to test that. For example, I have written the Verilog program for mux. The simple operation I'll take. I have written Verilog program for mux. How I will test it? Right? I'll apply different test cases. Test cases means different inputs. I'll apply input for I naught. I'll apply input for I1, and I'll check. I'll apply input for S select line, and I'll verify what is the output. If 0 0 0, right? If select line is 0, if I apply 0 0 0, so my Y should take I naught. What is value of I naught? 0. I should get 0. If I apply 1 0 0, right? My select line is 0, Y should take I naught. I naught is 1. Output I should get 1. If I apply 1 1 1, right? My select line is 1. My select line I should take I1. According to select line, Y should take I1. So I1 is 1. Output should be 1. So by applying, this is called as one test case. This is one test case. This one test case. Right? By applying different combination of test cases, right? We verify the circuit. We verify the design, not circuit. Sorry, design. What the Verilog program you have written, right? This Verilog program we will verify. That is called as functional verification. So functional verification is verifying functionality of design by applying different test cases. Okay? This is called as a design verification or functional verification. So to do functional verification, you should be knowing system Verilog and UVM. Then only you can do functional verification. Right? Functional verification just a step, right? To verify your design. But design is in what form? design is in Verilog or VHDL form, I can tell it is in the behavioral form. Design is in the behavioral form. So this behavioral form Foundry can understand. Right. So next what we do is in the synthesis step, we have synthesis. So can anyone tell me what is synthesis?
We convert RTL code into a gate level netlist.
Yes, good, right? Because my Foundry can understand only this one, right? It can understand layout of a cell, but layout we have not yet arrived. So before arriving to the layout, this behavioral description, it is in the form of if statement, case statement, assign statements, right? Thus we have to convert to the gate level form first. This Verilog or VHDL design is also called as RTL, register transfer logic. This we have to convert to gate level, right? That is called as synthesis. So converting gate level description, converting RTL to gate level description is called as synthesis. Right? You have RTL that you have to convert to gate level description. So to convert RTL to gate level description, right? So what are the inputs required? So to input required is one is RTL. This RTL is .v. No doubt in that. Next is what is required. You want .lib file. Right? .lib is also called as a liberty file. And one more thing is called as a .hdc file. HDC is called as synopsis design constraint file. Now what we are doing is, right, in the synthesis step, what are all the this one I had, right? I had the gate level and description. This is a gate. We have AND gate. Like I have one OR gate. After that I have inverter. Right? We have gate level and descriptions like this. This is net N1. Net is nothing but used to connect from one gate to another gate. That is called as net N2, N3. This is A1 pin, right? A2 pin, Y pin. This net N4. This is A1 pin, A2 pin, right? Y pin. This is OR gate. Right? This is net N5. This is A pin. A pin, Y pin, net N6. This is called as gate level and its connection, right? Gates we have and connected through nets. So N1, N2, N3, N4 are nets. Right? Now the question is, who is going to give you this gate information? Who is going to give you a gate information? For what gates you have to connect? Anyhow, your synthesis tool is converting your RTL, that what we wrote here by using Verilog or VHDL, that you have to convert into gate level. Right? What gate you have to convert? Whether you have to convert to AND gate, OR gates, NAND gates, or whether you can use D flip-flop, whether you can use MUX, right? That information someone has to give, right? Who is going to give this information? So that gate information, what gates you have to use for conversion, right? That gate information is present in .lib file. It has only gate information, right? .lib has gates information. There is one team called as a library characterization team. They will give this .lib file. Means what are all the gates you can use for synthesis, right? So what type of information you have for each and every gate? Each and every gate means, so each and every gate, or so we call this, instead of gate we call it standard cell, right? So standard cells are like basic cells which is required, like AND gate, NAND gate, OR gate, NOR gate, inverter, buffer, XOR gate, few complex gates like MUX, D flip-flop, AOI gate. AOI gate means AND or inverter, right? AOI gate, OAI gate, right? These type of basic gates which is used to build a circuit, right? These type of gates are called standard cells. They are called a standard cell because all the gates, all the layout of a gate, right? Every gate has layout, right? All the layouts of a gate has same height. Width can vary, right? The width can vary, but layout is having almost same height. Right? So for that reason, it's called a standard cell. So these standard cell information, right? For all these cells, the standard cells, we have information in .lib file. So what type of information we have? We have area, right? Delay of each and every cell. Each and every cell, how much delay it has. You have area information, delay information, and power consumption. Power information for each and every standard cell. Right? For each and every standard cell, we have this much information. In .lib file. In HTC file, we can give the constraint. Right? Constraint we can give, like what is the clock frequency. Right? Clock frequency. So you have like set input delay. You will study all these things. So what is the meaning of this? Set output delay. All this information you will see in .htc file. So by using these three files, right? See, because you should do synthesis, that is conversion from RTL to gate level description to meet this clock frequency, right? We have to meet this clock frequency. What are all the gates I have? The delay should be in such a way that the delay of the gates should be in such a way that it should meet this clock frequency. My design should, for example, I have given one, I have a clock like 1 megahertz or 200 megahertz clock I have in the design. So my design should meet this clock frequency. It should be ready with operating with 200 megahertz. Whether it can operate with 200 megahertz or not. To verify this, we have different checks, like setup check, we have hold analysis check, we have different checks we have. So the clock frequency information, like other timing constraint, like set input delay, set output delay, so that is present in HTC file. So by using this file, my tool will convert this RTL to the gate level netlist by picking the cells in .lib. It will pick the cells from .lib. So this much information is required for your synthesis tool to do synthesis. And what is the output of synthesis? Can you even tell me? What is the output of synthesis? Yes. Yes, output of synthesis is gate level netlist. So what is gate level netlist? It's in the what form? So gate level netlist is in the what form? What type of file it is? Whether it's a library file or a Verilog file or VHDL file, what type of file it is. It is also HDL file, like it can be Verilog or VHDL. Right? So .v is extension for Verilog, .vhd is extension for VHDL file. Right? So gate level netlist can be also in the form of .v or .vhd. Right? So RTL is also .v and gate level netlist is also .v. Like it's also hardware description language. Then what is the difference out of these two things? What is the difference then? See, RTL can have Boolean equations. Right? For example, in RTL, you can write Boolean equations like this. Right? Assign y is equal to a and b or with c. Right? This is a Boolean equation. You can have Boolean equation. You can have if statement. You can have case statement. Right? You can have like so that type of statements you can have to describe the behavior of a circuit. Right? That is what you are having in RTL. But in the gate level netlist, you should be having only gate and its connections. That's it. This y is equal to a and b. Here you have a and b, right? But in the gate level netlist, you should be having gates. Like you have a and b, it is connected through AND gate, and c is connected through OR gate. So in gate level netlist, we have only the description of gates. Right? Only we have description of gates. But in the RTL, you can have Boolean equations. You can have case statements. You can have right if statements. So by using all these things, we can describe the circuit in RTL. But in the gate level netlist, we should be having cells, cell names, and its connection. That's it. For example, you take this example, right? You take this example. For example, I have one input port here. I have one input port. This input port is also N1. All right. This input port is N2. This is N3. Both names are same. Input port and net name both are same. And output port I have, right? From this circuit I have output port. It's connecting to output port. Right? This output port name is N6. So I can write the even Verilog program for this, right? How to write Verilog program? I can write module, right? Like one example. Module name is example. Just I'll take any one module name. Then what are the input ports? How to declare first? N1, N2, N3, N1, N2, N3. This is a Verilog program. So and N6. Even I have forgotten to write N6 because N6 is also output, right? N6. Even this is also output. So next I have to declare what are the inputs, right? Inputs as N1, N2, N3, and output is right. Output is N6. Now you should describe the gate, right? Now this gate, I have AND gate. This AND gate is having like name as AND2. AND2. This name we have in the .lib file. .lib file has gate information, right? In .lib the name is for AND gate is AND2. AND2 indicates two input AND gate. And this gate also has some instance name. Instance name is U1. This is given by synthesis tool. Because in the design I can be having plenty of AND gates. So to differentiate between one gate to one AND gate to another AND gate, right? So we should be having instance name. Here also, right? This is the OR gate, the library name. In liberty file or library file, both are same. .lib. The name is R2 and instance name is U2. This instance name is given by synthesis tool. So the library name is inverter here, and right, the instance name is U3. So now you have see if we take this RTL, right? This RTL if we take, so RTL is like this: y is equal to, in RTL I will be having the Boolean equation for this. Y is equal to N1 and N2, right? N1 and N2 means N1 and N2 both are ANDed. So this ANDed output is done OR operation with what? N3, OR with N3. All right. And totally we are doing a NOT operation. Right. Totally we are doing NOT operation. So this is the Boolean equation. This is present in RTL. But here in the netlist we should not be having Boolean equation, or we should not be having if statement or case statement. Only I should be having gate and its connection. So the gate is nothing but this one, right? And 2. Gate library name. Library name is and 2. So next I have instance name. This instance name is given by my synthesis tool to differentiate between one gate to another gate. Because in the design I can be having plenty of AND gates. So to differentiate between one AND gate to another AND gate, so in synthesis tool has given a unique this instance name. So AND 2, right? Instance name is U1. Next you have port mapping, like dot A1. This dot A1 is connected to which net? N1 net. Dot A2 connected to which net? Right? N2 net. Dot Y connected to which net? N4 net. Over. This A1 is connected to N1 net, A2 is connected to N2 net, and Y is connected to N4 net. That is over. Next, OR gate. Take OR gate. Next we have OR gate. That instance name is U2. Right. It has A1 pin. This A1 pin is connected to which net? N4 net. Right. That you write. A1, N4. Next, you have A2 pin. Right. This A2 pin is connecting to which net? N3 net. Right. Next, dot Y is connecting to N5 net. Next, inverter. I have U3, right? Dot A connected to N5 net. This, right? A pin is connecting to N5 net, and this Y pin, right? Dot Y pin of inverter is connecting to N6 net. Right? This N6 net. Right? End module. So in this netlist, right, I have only gates, gate information. I'm not having any assign statements or if statements or case statements as we have in RTL, right? We don't have here. My netlist should be having only gates and its connection. So whether in this netlist what I have written, whether there is a connection from one gate to another gate, I have shown the connection. Can anyone tell me whether there is a connection? Yes. There is a connection between the gates in the Verilog program what I have written, gate level Verilog program.
No, sir.
Yes, others, whether there is a connection. There is a connection, right? You can see here this N4 net, right? This N4 is connecting to output pin of N4 net, right? It's connecting to output pin of your AND gate, right? That is U1 gate. This N4 is also connected to right input pin of OR gate, right? You see here this N4 is connecting in the netlist, right? Is connected to input pin of OR gate. This N4 net, right? This N4 net is output pin of your AND gate, and it is connecting to input pin of your OR gate. Same net. Then the meaning is what? These both have connection, right? It is the output, it is connecting to output pin and it's connecting to input pin. The meaning is the output of this is connecting to input pin, right? The connection is established. My tool can understand that there is a connection. Here also, right? This output of OR gate is connecting to N5 net. You see here that I mentioned here. And this same N5 net is connecting to A pin of inverter. The connection is established. You can see here the A pin is connecting to same N5 net. So it is output of OR gate and input to the inverter, right? Connection is established. My tool can understand this. Okay, then output pin of OR gate is having input connection to the inverter. So connection is present in this. Net connections are present from one output of one gate to input of another gate. So this is called as port mapping, right? This is called as port mapping. In a net list, right? So only this much information should be present in the net list. Even net list is also Verilog or VHDL file, but in a structural form, right? It should be having only gate and its connection. Gate and its connection. Only this much information you should be having in synthesis netlist. RTL is also .v and gate is also not .v, but RTL is in the behavioral form. But in the gate level netlist is in the gate and its connection. Only should be having gates and its connection. That's it. You should not use any other things. That is called as gate level netlist. So next, right, after synthesis, the next step is right physical design. See, before synthesis, after synthesis and before physical design, there is one more team is called as DFT team. DFT means design for testability. See, why this team? Can you tell me why DFT team?
For testing.
Proper distribution of power, sir.
No. Design for testability. Why? Why it is? Yes. Can anyone tell me why DFT team? Yes, good. For manufacturing defect testing. See, after chip is fabricated, I am talking when a chip is fabricated, not designed. Right? Chip gets fabricated. Now I have a chip. For example, I have designed a chip, right, for mobile phone operation. Right. A chip is coming out of a foundry. The chip came out. Chip has pins. It has come out of a foundry. I want to test this chip whether it is working or not. For that reason, I cannot connect to mobile phone module and I cannot test it by sending the images. Right. Because chip has to work properly in the mobile phone module, even it also requires software. To dump the software, like Android has to be dumped. Even there is a role of software also. Software also should do something, right? Only hardware cannot do everything. Even there is a software. So now how to test the chip, whether everything is fabricated properly or not. See, fabrication happens in nanoscale, right? If, for example, this is the metal layers which I want to fabricate, right? But while fabricating, right, these metal layers cannot get fabricated properly because fabrication is happening through chemical process. It is not like it is happening through grinding or something, right? It's happening in nanoscale, which the metal layers even we cannot see through our eyes. We can see only through complex microscope. That much small they are. So while fabrication, what metal layers may happen is they will bulge like this at some areas because of improper cutting of metal layers, right? Even this layer may bulge, right? So these two metal layers get shorted. They are shorted during fabrication, right? Due to variation in fabrication, they may get shorted, which the foundry can't identify whether they short or not. Sometimes, because how much metal layers I will be having in the design? I will be having metal layers in more than 10 lakhs. 10 lakhs, more than 10 lakhs metal layers will be running inside the chip. How to identify where there is a defect? I cannot identify easily. If there are one or two metal layers, right, I can identify. There are more than 10 lakhs metal layers. Some metal layers may be like, it may be shorted like this. Now the question is, right, if this happens inside a chip after fabrication, how to check it, how to validate it, whether the chip is proper or not? That we do by applying some test cases. We'll apply some real test cases like 1011, some test cases we apply. We'll check those test cases at outside, right? So to apply these test cases and to verify those test cases, right, the design has to be slightly modified, right? So I should modify the design so that it can be tested. Design can be tested easily. Right. After netlist, right? After synthesis, if I use the netlist directly for physical design, I'll generate a GDS2 file. I'll send to the foundry. Right. This design may not be tested. Right. That means there is no flexibility of testing the design. We have not given a flexibility inside the chip for testing purpose. So we have to have some flexibility inside the chip for testing purpose. They have to add some additional circuitry. These circuitry are responsible for testing the chip after fabrication. So to adding this additional circuitry, right, that is the responsible of DFT team. They will add this additional circuitry. They will modify the netlist by adding some additional circuit inside the netlist without affecting the functionality. Functionality should not be affected. Right? Why they are adding some additional functionality so that chip can be tested after fabrication. For testing chip after fabrication, they are making the changes in the circuit now only, during design phase only. They are making the design in such a way that the chip can be tested after fabrication. Right? That flexibility they are introducing inside the chip. So that is the role of DFT team. So what DFT team is doing is they insert additional logics inside by modifying netlist, so that functionality is not varied, right? Functionality should not be disturbed. Is not disturbed. Without disturbing the functionality. Functionality is not affected, I can write. Without affecting the functionality, right? They will add some additional logic, right? So that, right, this is done so that chip can be tested after fabrication. We can test the chip after fabrication. For that reason, we have DFT team. So they will use different methods like scan chain insertion. You will study what is the scan chain insertion. Only this you will study in PD, because even PD also we want this. What do you mean by scan chain insertion? Then they will do built-in self-test. Next is ATPG, automatic test pattern generation. Right. These things they will do in DFT. So they will add all these things in our chip. Sorry, not in chip, in the netlist. Right. So that this netlist is converted to GDS by the PD team. And these things are also incorporated in the circuitry so that chip is easily tested. So they should incorporate this scan chain, and they should make the chip right. They should insert built-in self-test. They should include the module for automatic test pattern generation. All the things they can include without affecting the functionality. They should not disturb the functionality. Right? That is the role of DFT team. The name only tells, right, design for testability. Make the design ready so that it can be tested after fabrication. So testing the chip after fabrication is called as what? Can anyone tell me what is the meaning? What we call that step as? Testing the chip after fabrication. See, making the circuit ready to test the chip after fabrication, that is called as DFT, design for testability. Make the circuit ready or make the design ready so that it can be tested after fabrication. That is called as DFT. But testing the chip after fabrication is called as what? What step is that? No, it is not physical verification. Physical verification is testing the layout, right? Not the fabricated chip. Real chip is tested. Physical verification is either design. It is done after the design is completed. We are verifying the design by using physical verification. We will not test the chip. So testing the chip after fabrication is called as post silicon validation. Right? It is called as post silicon validation. Right. See, these steps are important, right? They will ask, at least, even though you don't know the concept of DFT or this one, right? Functional verification properly. At least you should be knowing what are the steps included in ASIC design flow. So this question is mainly asked in interviews many times. What is ASIC design flow? Please explain. See, you can explain PD flow, but till this, right? PD flow, next the PD will start. So before this, you should be knowing all the steps. At least why these steps, right? You should be knowing that. So next is physical design, right? Next we start with physical design. So now what is role of physical design? Now you can tell me what is role of physical design. Now the design is in what form? Right? After synthesis, my netlist will go to DFT and it will come to physical design. Now design is in what form? Can anyone tell me? Now design is in what form?
Gate
Yes,
level
after
netlist.
synthesis. Yes, after synthesis, design is in gate level form. I can tell, right? It is in the gate level netlist form. Right? So this gate level information your foundry can't understand. Foundry can understand only layout level information. So in physical design, we convert this gate level information to layout level information. Right. We convert this gate level information to layout level information. So we will not call that directly as layout level, we'll call it as physical level. Right? We call it as physical level. So that is the role of physical design team. Right. So to do physical design, right, we want layout information of a cells. For all the standard cells, we have area information, delay information, and power information in .lib. Right. Similarly, there is one more file called as LEF file, .lef file. This .lef file is called as layout exchange format. Layout exchange format. It has gate. It has layout of a gates. Right. It has layout of a standard cells. For all standard cells, this file has right layout information. See, not complete layout information, only the layout, right? In this layers, I don't want this diffusion layer for physical design, right? Those informations are not present. Only what are the information is required for each and every cell, like polysilicon, like metal layers where it is running. So the which is a few information which is not required for physical design that is not present in LEF file. For foundry, we have to send this complete file. All the layers should be present. All the layers are present in GDS file. So for every cell, every standard cell, I'll get two files. Right. I'm not talking about complete GDS. I'm talking about cell GDS. I'll get two GDS, two files. One is LEF file. So LEF file is abstract layout information. Abstract layout information. Abstract layout means we have the layers only which is required for physical design. Only that much layers. For physical design, I don't want this diffusion layer. I don't want this right implant layers. I don't want. So those information will be removed and it is given for physical design. So that much information is present in LEF file. So there is one more file called as GDS file. For each and every standard cell, I will get this file, GDS file. So this GDS file contains full layout information of cells. Complete layout information of cells is present in GDS file. After physical design, all the cells I will replace by GDS view. All right. And that then I will send it to the foundry. So LEF file, we don't have complete layout information, only the few layers which is required for PD, right? That we have. Because to save memory, unnecessary memories, for that reason, we use LEF file in physical design. So even if you remove unnecessary layers, right, even runtime will increase by runtime. For that reason, we use LEF file. So this LEF file or GDS file, right, is given from layout team. They will draw the layout for each and every standard cell, and that layout information they will give in this file, LEF file. Now for in the standard cells, for all the standard cells, so we have .lib file, even we have LEF file. LEF file has layout information, .lib has area, delay, and power information. Right. Now this physical design, I already told you, right? We convert this gate level information to the physical level, right? So it has following steps to convert the physical information. So can anyone tell me what are the steps? What are steps for physical design? Can anyone tell me?
Floor planning,
Yes. See, I'll just mention what are all we doing, right? We will do floor plan. Right. Next is placement, clock tree synthesis. Next routing. Right. Next is physical verification. So these many steps we have for physical design. Floor planning, placement, clock tree synthesis, and physical verification. So what is floor plan? Again, floor plan has a few steps. Right? All the steps we'll study. See, before this, we have to study all input files for PD. This we'll study, right, in the course. Next, we'll study difference between right difference between full chip level design, and block level design. Right? So full chip means, see, the entire chip we cannot do physical design for that. Right. So for entire steps, right, we cannot do physical design. Entire chip. This is a full chip. So what we do is this full chip we will partition into different blocks. This full chip we will partition into different blocks. This is one block. Block A. Right. This is another block. Block B. Right. Next we have another block like block C. Next we have another block. Another block I have. This is block D. Right. Here I have another block. Block E. Right. Different blocks I have here. So a full chip is divided into different blocks like block A, block B, block C, block D, block E. Right. This full chip, different blocks. This each and every block is given to one engineer. Right. The engineers will do physical design of each and every block. Right. For each and every engineer, the separate netlist has been given. The entire netlist is divided into different small netlist, and for each engineer they'll give the netlist A, B, C, D, E. Right. They'll give the netlist. and the block level engineers will do physical design of each and every block. Right? This you will do till the experience of 5 or 6 years. After that, you will handle full chip, complete chip. To full till 4 or 5 years, right? You will do the physical design of each and every block level design. After completing the physical design for each and every block, your full chip designer will integrate all the blocks. They will make connection between all the blocks. He will generate a GDS file. Then he will send to the foundry. So this is called as full chip level design. And this each and every block, if I do PD, right, that is called as a block level design. So first we'll understand, right, difference between full chip level design and block level design. So this step is called as partitioning. So first you will understand all the input files for a PD. When a PD course starts, right, all the input files. Here we have seen only 2 files. So there we'll understand all the input files for physical design. So next we understand how to do partition, right? What is difference between full chip level design and block level design? How PD is done for full chip, right? Means the integration of blocks. What varies from full chip level design PD to block level design PD? That we'll understand. Next, we will do block level design, right? In for one block level design, we'll discuss all these things. Block level design, right? We'll discuss all these things. What is floor plan? What is placement? What is CTS? Right. Next, what is floor planning? Floor planning includes following steps: creating core area, right, and die area. Right. What are the parameters? What do you mean by core area and die area? Right. If I for the block level design, right, I have to draw core area and die area. Even I can draw for any shape. Even the shape what I gave, right? This, for the L shape also I can draw core area and die area. This inverted L shape, right? Not L shape. For this also I can draw core area and die area. This is core area, and even I can draw die area. Right. This is called as core area. And this is called as die area. So we will study how to create this core area and die area. What are the different parameters, right, describing this core area and die area? Like we have utilization, aspect ratio. So we have def method. Right. We have coordinates method. So what are the different methods we have to form this core area and die area? So that we will study, right, in this step. That comes under floor planning, right? Creating core area and die area. So next is, right, port placement. Port placement means the input and outputs of a block. This block, complete block, the inputs and outputs of a block is called as ports. All right, we'll place the ports here. Ports are placed in between core area and die area. So inputs I'll place somewhere here. Outputs I'll place somewhere here. Right. Again, this input and output, right, port placement depends upon the full chip. For example, my block A is communicating with outside world signals. So I'll place here so that I can easily make connections here. And output of A is going to B, block B. So all the output ports I have to place here for A block in this region, so that I can make easily connection to block B. So based on the full chip placement of a blocks, right, where the blocks are placed in full chip, based on that I should do the port placement. That information I should get from the full chip level designer. See, full chip level designer is called as chip top. So based on him, right, I should do this port placement. These ports are simple metal layers. They are simple metal layers. So these ports is responsible for taking the input signals inside to the block, right? They are responsible for taking input signal inside the block like this, and signals go outside the block through the output ports. Right? It will come through input ports and it will go through output ports. Right? This is input ports. Next it is the output ports. So according to the full chip designer requirement, according to full chip designer requirements, we will place the ports, these ports. That is called as port placement. So after port placement, we have macro placement. So what is macros? Can anyone tell me what are macros?
Small design particles.
No, what is macros? See, macros are complex cells, right? Macros are complex cells. We directly use, right? We directly use in our design, right? Design, right? Without writing the RTL. We did not write RTL for this. Without writing the RTL program for this, right? We will use these complex cells because these cells are already optimized. These cells are already optimized. See, I will give you one small example. All right. So before seeing this, right, we'll take a 10 minutes break. Now time is 11:40. So we'll continue again at 11:50. Right? Then we'll discuss what is macros. Right. We'll start at 11:50 again.
This conference will now be recorded.
Okay, we'll continue now. Right. I was discussing about what, so this one, right? What is macros? Right. So we have few circuits in the design. Right. Like macros are complex cells which we directly use in our design. Right. These are cells are already optimized. Right. This macros, I cannot call this a cell. Inside it we have many cells. These macros are already optimized. So we use macros because our complexity gets reduced. First of all, right. Second thing is we have very less runtime. See, for example, I will give you one example, right? Everyone, I will just give you why we use macros in the design, how it is useful. For even macros also, I can write the RTL. I can do synthesis. After doing synthesis, I can do physical design. Even I can use in my design. I can do that. But we will not do that. We will not write the RTL for macros. Directly we use in our design directly. Directly we'll make the connections in our design. So the reason for that is, right? It is like already this circuit is already optimized, right? This is the best circuit. For this reason, I'll give you an example, right? So you are preparing many dishes in your home. Just I'll give you an example. Many dishes you are preparing in your home. You have to create rice, sambar, right? Something and all you have to create. So you have to even create, right? You want to even prepare puliogra. Even you want to prepare some bisibele bath, right? Something you have to prepare. So you have a lot of things, and for a lot of things you'll start from the scratch. From the beginning you start. For sambar, everything you will start from the beginning and you will create everything from the beginning. But for puliyogre, what you do for saving your time, you will already bring right the famous puliyogre powder from the shop because you feel that that powder is better, good, right? It's already optimized, that powder, puliyogre powder, like MTR or GRB. I am not the I am not doing advertisement of these brands. Just I am telling you example. So we have many brands like MTR or GRB. We have many brands. We'll directly purchase that from the shop. Even for those things, puliyogre and that bisibele bath powder, right? Even we can do from the scratch. No issues. We can do that. We will not do that for two reasons. One is time wasted in doing that from the scratch. Second thing is we are not sure that we are going to get the same taste when we do from the scratch. A rasam powder, right? We have many powders. So from the famous company, which the company tells that we are going to give you the best taste, we'll directly purchase from the shop and we'll directly mix with our rice. And this puliyogre powder is like a macro because this powder is already optimized. And this powder, they'll tell that it is a best thing, right? We'll directly we'll purchase from the vendor. Those are called as macros. Few circuits, right? If we write the Verilog code from the starting, if we do synthesis, if we start doing physical design, one is complexity increases. For example, I have, just you take one example, I have 10 SRAM in my design. Right? 10 macros I have, just to assume. Right? This macros I have placed like this. 10 SRAMs I have. These are all macros. SRAMs are macros. These macros I have placed. Each macro is having like 2000 cells. Right? Or else, for example, each macro is having 1000 cells, you assume. For 20 macros or for 10 macros, I'll be having 10,000 cells extra in my design. For these 10,000 cells, I have to do PD. Right? So instead of that, macro is already done. This macro, SRAM macro is already designed, and I will purchase this macro from the vendor. he tells that my macro is best. Right? I'll directly purchase from the vendor, right? I'll purchase .lib for this macro. I'll purchase a .lib. .lib has timing information. I'll directly purchase the LEF from him for the macro, for SRAM macro, and I'll purchase a .gds file. I'll purchase these 3 files from a macro provider. And these macros I'll directly use in my design. And I'll make the connections between them so that I can reduce the cell count. And my vendor tells that this macro is best macro. It can operate with high speed and is having less power consumption. He's already taken care. So my effort reduces to make it as a best macro. So for that reason, few cells we directly purchase from a vendor. Right? These complex cells are called as macros. So next step is macro placement. So we will see what are all the guidelines for placing these macros. See, first we do macro placement because they are less in number compared to standard cells, right? They are less in number. For example, if I have 60,000 standard cells, macros will be like 40 or 50. That's it. This 40, 50 cells, first I'll place it. Right? There are different guidelines for placing these macros. First I'll place these macros. Right? That is called as macro placement. So generally we have macros like SRAM, right? In physical design, PLL, phase lock loop. We'll use macros like phase lock loop. So these type of macros generally we use in block level design. These two macros. So if I use only one SRAM in the design, right, I can write the Verilog code. Hardly it has 1000 cell extra, no issues. I'll do from the scratch, no problem. But I have 10 to 15 SRAMs if I want, then it will add up. The will be why to do that. So for that reason, what I'll do is I'll directly take the layout information and I'll place here. So this is layout of a macro. Right? What I'm placing here is layout of a macro. I'll place inside core area. So these are all macros. So this we do it in, right? What step? Macro placement step. So next we have is power planning. So one student asked me whether power planning is different step. So it comes under floor plan only. So here we do power planning. So in power planning, we'll see how to do the power planning so that all the cells, standard cells and macros get VDD and VSS, right, without IR drop. In power planning, we see that all cells means gates. Another name for gate is cells. All cells and macros gets VGD and VSS connection without IR drop. So what do you mean by IR drop? What do you mean by IR drop?
Current and resistance.
So now in physical design, what is IR drop? For example, I have a VDD port here. Just to assume I have a VDD port. I am getting VDD from here. Just assume that. I am connecting from VDD from here to this macro. I'm making the connection. So this is metal layer, right? What is this? This connection I'm making through metal layer. This is metal layer. By using this metal layer, I'm making the connection to macro. And similarly, I'll do VHS also, right? I'll do VHS connection to the macro. Right? VHS will ignore for the time being. So we'll only consider VDD I've done. So here, this I will redraw. This is your VDD. This is your VDD port. Right? This VDD is having 2 volts. And this is a macro. This macro is connecting to VDD. Right? Here it's connecting through metal layer. This is a metal layer. Here also I should get 2 volts, right? I should get 2 volts. But what happens is this metal layer has resistance. And when this macro is switching, the current will flow to the macro. So because current is flowing and this metal layer has internal resistance, so because of this reason, there is some IR drop. IR drop means the drop, the voltage drop happening on the metal layer. It's called as IR drop. In physical design, we call IR drop means the voltage drop which is happening on the metal layer. Ideally, it should not happen. But because metal layer has internal resistance, this drop will happen. So out of 2 volts, 0.3 volts will drop here on the metal layer. So only I will get remaining 1.7 volts here. Right. For this macro, I am getting only 1.7 volts because 0.3 volt is already dropped on this metal layer. Here also we have V is equal to IR, right? On the metal layer. Metal layer has some resistance. And current flows means it will create some voltage drop on this. Out of 2 volts, 0.3 volts will drop here. Remaining volts will reach to the cells. This is called IR drop. So for this reason, to mitigate this IR drop or to reduce this IR drop, we have to reduce this. Right? To reduce this IR drop, we do power planning. So how to do power planning? While doing power planning, we'll create rings, straps, rails. Right? How to do that? So that we'll discuss. Right? So after floor planning, right, we'll also study about STA, static timing analysis. In static timing analysis, we discuss about what are different types of clocks. Right? We discuss about what do you mean by skew, right? Latency, right? Uncertainty. What do you mean by skew, latency, uncertainty of a clock? See, IR drop is nothing but this is the 2 volts. At this VDD, I am getting 2 volts. Right? This is 2 volts. This 2 volts I should get at the cell, right? But as this metal layer, I am using metal layer for connection. This metal layer has resistance. So because of the resistance present in the metal layer, right? Few voltage out of 2 volts, few voltage will drop on this metal layer. Right? This metal layer is having some like 0.3 volts voltage drop. All right. So out of 2 volts, 0.3 volt is dropped on the metal layer. Remaining 1.7 is going to reach to the cell. So I expect 2 volts to reach to the cell, but instead of 2 volts VDD, I am getting only 1.7 volts VDD. Right? Because I have resistance on the metal layer, right? When the current flows, I have resistance on the metal layer. When the current flows, there is some voltage drop happens because V is equal to I into R. The voltage drop happens on the metal layer also because the metal layer has resistance. So because of this reason, all right, there is a voltage drop on the metal layers. Out of 2 volts, 0.3 volts is dropped here. Remaining 1.7 volts will get here. So this is called as IR drop. This IR drop you have to reduce. We have to see that less IR drop happens on the metal layer. We cannot make it 0, but we should see that less IR drop is happening on metal layers. We should design a power planning in such a way that less IR drop is happening on a metal layers. That is called as IR drop. You got it? What is IR drop? Right. So next is in this we'll discuss about skew, latency, uncertainty, right? So here we'll also discuss about setup analysis, hold analysis. Setup and hold analysis. This is for rest to rich path, right? Into rich path. Next we'll discuss for out to rich path. So we'll discuss about multi-cycle path. What is multi-cycle path? What is half cycle path? So we will discuss about PVT conditions, how these PVT conditions affecting setup and hold analysis. How these PVT conditions will affect setup and hold analysis. Right. We'll discuss about asynchronous design, how to handle timing for asynchronous design. All these things we will discuss in STA. So after discussing this STA, right, then we will discuss about placement. So this you will study in STA, all these things, all these concepts. So next is, right, after power planning, next is placement. But in the course, right, after power planning, right, we'll study about STA. After studying STA, then we'll go to the placement. Because after placement stage, we have to do STA. So for that reason, you should be knowing what is STA. What is placement? Placing all standard cells inside core area. Right? Till now, we have placed only macros. Only macros are placed. Right? So placing all standard cells inside core area is called as, right, placement. So here we'll place all standard cells. Standard cells means we'll place layout of standard cells. Right? We'll start placing all the standard cells like this. So standard cells count will be very high, like 52,000 standard cells, right? So place all standard cells inside core area. This is called as placement. So after placement, we will do many checks. After placement, we will check what is congestion. So we will study how to do these checks. What is congestion, right? So in placement also we will study, right, different types of placement. So how to do the best placement, right? That you will study. So after placement, so you will do congestion analysis. So congestion analysis will enable you that whether these cells can be routed or not, whether they will get sufficient space for routing or not. Right? Routing means connecting all the cells, right? So connection is not yet done. Only I have placed layout of a cells here. So connecting the cells is not done. So whether these cells can be connected or not without any problem. That is called as that is done by congestion analysis. So next we do max cap and max trans analysis. That you study. Max cap means max capacitance and max transition analysis. In short, we tell as a max cap and max trans analysis. So here after that we will do setup analysis. So here we will not do hold analysis. So then you'll understand why we will not do hold analysis after placement. Right. So here we are going to do setup analysis. So these are the checks you will do after placement. Right. So first you will place all the standard cells inside the core area by using best method. And after that you will do all these checks. Right. If these checks are okay, right, then you will proceed for clock tree synthesis. Right. So what is clock tree synthesis? Can anyone tell me? What do you mean by clock tree synthesis?
Distribution of clocks to all the sequential circuits.
Distribution is already happened in the netlist, right? In netlist only we have clocks. It's already distributed. Why you have to do again? I have a clock port here. Right. I have a clock port here, right? And I have flip-flops. Like for simplicity, I'll use 5 flip-flops for simplicity, right? I have 5 flip-flops, and I have clocks here. Connecting this clocks to the clock port is already done. We've already done this connection. Why we have to do again? Why it is required? This is already done in the netlist. Netlist, this is already done. Why we have to do again? Why this CTs has to be done?
It checks the signal reaching all part of the system.
Now it is reaching, right? Now the clock port is connected to all the clocks. Now it is reaching only. It's already connected now. So the clock port. So the problem is, right, this load on the clock port is very high now. This clock port, the load is very high. Load means what? See, all the spin capacitance, right? The spin capacitance of each and every clock. Every clock has spin capacitance. Pin capacitance along with this net capacitance. Net means metal layer. Even metal layer has resistance, and metal layer also has capacitance, because this is metal layer, right? And we have ground. So this will form a small parallel plate capacitor. Its value is very less, but even it's going to form on capacitance. This net capacitance and this pin capacitance. Every cell has pin capacitance, because every cell, if you take, right, if you see the cell, you have source, drain, right? After that you have silicon dioxide. On top of it you have gate. For gate, if you take NMOS, you will connect positive voltage to the gate. In between we have silicon dioxide. In the channel we have like electrons. So here it will form on parallel plate capacitor. So this capacitance is also found in MOSFETs, right? Gate, silicon dioxide. Silicon dioxide acts like dielectric, and again channel negatively charged. It will form parallel plate capacitor. So those capacitance is called a spin capacitance. So in the design, in the real design, I will be having 10,000 flip-flops. Right? In the real design, I am having 10,000 flip-flops. So this, first understand why this CTS is required. So 10,000 flip-flops if I have, each flip-flop is having 0.5 Fermi or 1 Fermi farad only you take. Each flip-flop is having 1 Fermi farad of capacitance, pin capacitance. So pin capacitance is only 1 Fermi farad. What is the total capacitance? What is the total capacitance? Total load capacitance. See, this load capacitance for the clock port is nothing but sum of all pin capacitance plus net capacitance. Net capacitance will ignore. Only will consider pin capacitance. If each flip-flop is having like 1 Fermi farad of pin capacitance, just for simplicity, if I have 1,000 flip-flops, not 10,000, we will assume 10,000 flip-flops. Then what will be the load capacitance on the clock port? 1000 Fermi-farad, right? 1000 Fermi-farad of capacitance I have on the clock port. All the pin capacitance, now it has formed 1000 Fermi-farad of, all right, load capacitance to the clock port. Now we have to charge this capacitance completely. Then we see this is a clock signal. This is the clock signal. Right? It is on time and off time. We have to charge this load capacitance completely. Then it is called as, then we'll get on time, right? Charging. Right? I have to charge this load capacitance completely. So charging the load capacitance, this much load, 100 Fermi farad, will not happen in fraction of seconds. It will take some time. Right? It will take some time, and it will charge. Again, when I want to get low level, this capacitance has to be discharged. In the block level design, I am seeing only port, but in the full chip level design, this port is driven from some other cell. This cell is responsible for charging and discharging this load capacitance. Now it has to be discharged completely. In the full chip level design, this port is driven from some other cell. Now this has to be discharged completely. Discharging happens, right? It's taking more time to discharge. The reason for this is what? Because of huge load, right? Because of huge load on the clock port, right? It is taking more time to charge and more time to discharge. So if it is taking very much huge time, right, to charge and very much huge time to discharge, so the square wave is converted to triangular wave. So this we call it as rise time, right? This we call it as fall time. Or this we call it as rise transition, this we call it as fall transition. So more load on the clock port will lead to high rise time and high fall time. This may be because of two reasons. One is pin capacitance. This clock port is directly connected to all the cells which is having high pin capacitance. And this pin capacitance will lead to high load capacitance. First thing. Second thing is net capacitance, right? So for example, this flip-flop, if you see, you have more net capacitance. So even this net capacitance is going to form huge load. So charging and discharging will not have right proper. It will not happen in short amount of time. It will take huge time. So in this clock signal, I don't have pulse only, right? On this is called as on pulse. This is called as off pulse. I don't have this pulse only. If pulse is not there, flip-flops may not work properly. So to meet this clock transition, right, what I want to do is I should be having only small amount of rise transition. I should be having only small amount of rise transition, small amount of fall transition. Right? This is rise transition. Right? This is fall transition. Right? I should be having at least minimum on pulse. This is called as on pulse from here to here. This is called as off pulse. In the clock signal, minimum on and off pulse should be there for flip-flops to work properly. So to maintain this, I should be having less rise time, less fall time. So for that reason, what we do is we will start building the clock tree. I'll just explain for these 5 flip-flops. Right. So how to build a clock tree? Right. Take from this, insert 2 buffers here. Right. So now these 2 buffers I'll connect here. Right. Right. So now the load on this clock port, right? This clock port, the load is reduced. Right. So because the load on this clock port is only pin capacitance of 2 buffers. That is the load on the clock port. Instead of 1000 fermifarad, I have only 1 fermifarad, 1 fermifarad, only 2 fermifarad. So less capacitance, I can have more. I can charge the capacitance very fast. I can discharge very fast. Right. First thing. Right. So now I want to this buffer, right? This buffer now. This is the role of the buffer to connect to the next cells. So this buffer is connected to this cell. Again, I have to connect to this cell. But if I connecting from this cell to this cell, I have more net length. This net length may result in higher drop, as I discussed. Right? More net length, more resistance, and even more net length may have more net capacitance. This net capacitance, again, it will create the load on this. This effect can be seen here also. So for that reason, what we do is I will use one more buffer here to break the net, right? I'll use one more buffer here. Now net length has become small, this much net length. Role of this buffer is completed. It's connecting to this cell and connecting to this cell. Now this cell will take care about connecting this. Right? Again, I have to connect from here to here. Right? Again, it's very difficult because it will create a more net length. Right? Again, use one more buffer and connect from here to here. Now load on this buffer is right pin capacitance of this flip-flop and pin capacitance of this buffer, and load on this buffer is pin capacitance of this flip-flop and pin capacitance of this pin capacitance of this buffer. Load on this buffer is right pin capacitance of this flip-flop. That's it. So every buffer is having at least a very minimum load. Even net length is also reduced. Again, I have to connect here. This flip-flop I have to connect. I'll take here. I'll take one more flip-flop, one more buffer. I'll connect here. Now load on this buffer is right pin capacitance of this, pin capacitance of this, and pin capacitance of this. These three pin capacitance and net capacitance. Right, that is load on this. So everywhere the load is reduced, right, so that I can get rise time and fall time. Rise time and fall time can be very small because on each and every cell we have reduced the load, but delay may increase. The clock, this for example, if this clock edge, right, this clock edge, for example, this clock edge, I am getting here at 0 nanosecond. But the same clock edge, right, it will reach to this flip-flop C. This is A, B, C. It will reach to flip-flop C. After how much delay? This buffer delay, this buffer delay, this buffer delay, and net delay. Right. After this much delay, it will reach to this flip-flop, C flip-flop. So same edge I'll get after some time. I'll get the clock signal here. It is delayed. Right. I'm getting after some time. Right. This delay is called as right insertion delay or latency. So because of this, there is an insertion delay or latency. Latency or insertion delay means time taken by the clock signal to reach to the clock pin of the flip-flop from the clock port. Input and output of a block is called as port. This is called as port, clock port. This is clock pin. So here if I get at 0 nanosecond, after what nanosecond the same clock edge will reach to pin clock C. It will reach after 2 nanosecond. Right? Then 2 nanosecond is insertion delay for C. So insertion delay will change from flip-flop to flip-flop. So here if I get clock edge at 0 nanosecond, for B, right, I have only 2 buffer delay. So it may reach here after 1.5 nanosecond. Here it may reach immediately after 1 nanosecond. The delay increases. This delay is called as insertion delay or latency. So for this reason, right, to reduce the load on the clock port, right, we do clock tree synthesis. Means build the clock tree, right? Now the clock tree has built. This is connected to two buffers, and this buffer is connecting to one flip-flop and another buffer, and this buffer is connecting to one flip-flop and another buffer, and this buffer is connecting to the flip-flop. A clock tree is built, right, in the clock path. So this is called as clock tree synthesis. So clock tree synthesis means build clock tree by using buffers and inverters. I can use back-to-back inverters. Instead of using one buffer, I can use back-to-back inverters. Even that will do the same operation, right? Back-to-back inverters will give you the same signal. That is called as clock tree synthesis. So it is done, right? It is done to reduce load on clock signal or load on the clock output. Load means the capacitance value. That is called as load, or to reduce the fan out on the clock port. So after CTS, right, what checks we will do, that we will study. So now in CTS, we will study how to do CTS. What are the different factors we have to do before doing CTS? Right. That we'll study. After that, after CTS, we'll do many checks. So these are all the common checks which we do at every time. Setup and hold. Here we'll do hold also. Hold check. After that, we will analyze what is latency, how much latency has introduced. Right. We'll analyze skew. What is skew? We will check minimum pulse width, right, is maintained or not. Minimum pulse width violation. So whether there is any duty cycle distortion. So duty cycle distortion is not required. Minimum pulse width is sufficient. Right. So these are all the additional checks we do after CTS. Like what is latency, what is skew, minimum pulse width. Minimum pulse width means every clock, right, the clock reaching to every pin, it has minimum pulse width or not. This is the, see, actual clock means it is having rise time, right? It is having fall time. Like this is actual clock. This is called as minimum on time. This is called as minimum off time. Whether every clock is having either the clock reaching to every flip flop, which is having minimum off time or minimum on time or not, that we will check. That is called as pulse width check. So these are all the different checks we'll do. This we study. Right? We'll study clock tree synthesis in detail. So next we'll study about routing. What is routing? Connecting all cells by using metal layers is called as routing. Now what we do is we have standard cells here. We have standard cells. All these standard cells are connected through routing. Connect through metal layers, right? All the standard cells, macros, right, and ports also. Right? For example, these ports are first connecting to the standard cells, right? Even make these connections. So connect all the standard cells, because connection is not yet done. Only we have placed inside core area. Now connections we have to do. Right? So connecting all the standard cells, all the cells, right? All the cells means standard cells, macros, and ports by using metal layer is called as routing. Okay. So after routing, right, all these checks will do. Congestion is not required because routing is already done. So all these checks you do. Same again, you will do all these checks. These two checks. Skew, latency, all these things you will do only after this, right? You will do all these checks. Apart from that, you will do two main checks here, DRC check and LVS check. DRC and LVS check you will do. DRC means, right, whether all the metal layers are routed, all the metal layers are routed with minimum spacing or not. There is a file called as a TF file. So TF file has rules, all the rules. Rules means between one metal layer to another metal layer, you should maintain minimum spacing. So the spacing should not be less than this. Right? This minimum spacing, right, should be minimum. We should maintain this minimum spacing. If the spacing goes less than the minimum spacing, then there is a violation. So you have minimum width, right? The metal layer should have minimum width. There are some wire rules, right? So all these things are maintained or not. Right? That check we do. So DRC stands for design rule check. Right? Next LVS, right? LVS stands for layout versus schematic. Layout versus schematic. So layout versus schematic means, so we have layout here. This is layout. Right? Standard cells in connection is called as layout. Schematic means netlist, right? This is netlist. So what are all the connections present in the netlist? The same connections are maintained in layout or not. That is called as layout versus schematic. So layout versus schematic, right? We compare netlist with layout. That is called as layout versus schematic. Compare netlist with layout. So what are all the connections present in the netlist? The same connections should be present in the layout. If that is there, no issues. If that is not there, then there is a violation. So that is called as LVS. So after LVS, right, instead of physical verification, I can do after this doing routing, right? We will send our block for sign off checks. There are separate sign off checks team, right? They will do this sign off checks. Sign off checks team means like IR drop and power analysis team. IR drop and power analysis team. Separate team it is, right? It is like Red Hat team. They use separate software called as Red Hat, and they will verify what is the power consumption, total power consumption of chip. What is the IR drop? I have explained what is IR drop, right? How much IR drop is happening, whether this IR drop is minimum or not, or whether it is in the limit or not. If there is more IR drop, and they will intimate us, here you have more IR drop, so please do some changes. Then again we have to check why there is more IR drop, whether our power planning is proper or not. Right? We have to verify that. So first we'll send the block to IR drop team. They will check IR drop and power analysis, and they will communicate us. They'll send the reports. Like in this region, you are seeing more drops. So please verify it. So next is, right, you have timing sign of team. Timing sign of team, right? The same checks whatever we have done right here. The same checks, they will do STA, static timing analysis. Even STA can be done here also. After CTS, after placement, after routing, we can do STA, right? For physical design, we use a tool called as, right? For physical design, we use a tool called as ICC2. Here tool we are using is ICC2. In IGC2 only we can do all the STA checks we can do, but again we'll do by using sign up tool, that is called as prime time, because it's accurate, because this software is built only for this timing purpose. But IGC2 is built for all the purpose, STA and doing power planning, for doing placement, for doing CTS, right, for doing routing. It is built for multiple purpose, but prime time is built only for timing purpose. So this tool is accurate and fast. Right, here we do STA, static timing analysis. Then there is separate team called as physical verification team. Even this team will do like DRC and LVS check again. They will do DRC and LVS check. DRC, right, LVS, and electrical rule check. ERC I can tell, right? Electrical rule check. Electrical rule check means whether all cells are getting VDD VSS or not. Whether all cells get, right? All the cell has input pin. Whether this input pin is connected or not. It has to connect to output of some cells, right? Whether it is connected or not. So like that, they will do some electrical rule checks, whether all the cells are getting VDD or not. VDD and VSS are connected to all the cells or not. They will do this ERC check. So these three checks they will do in physical verification. Again, they will use separate tool here. This tool is called as Caliber. This is from Mentor Graphics. They'll use separate tool called as Caliber, and they'll do all these checks. So when your block is passing all these checks, right, then you can send for integration. Your full chip designer will integrate, right, and he will send to the foundry. He will create GDS2 file. For the full chip, he will create GDS2 file. So next step is integrate, right? Because this you are done for block level, right? So then you should do full chip level design. Means it is integration of blocks. To integrate all the blocks. After integrating of the blocks, create GDS2 file. So this GDS2 file has only layout information, right, of cells and its connections for the entire chip. Right? Create GDS2 file. Then you send to foundry. So this is called as, this we are not doing full chip level design. So but we are doing from here to here, right? So from here to here till sign off checks will do. This is what we are doing in physical design for the block level design. Starting from understanding the input files, right? We will go to floor planning. Then we'll understand what is STA. Right? Next we'll do placement. This only is called as STA, right? Setup analysis, setup and hold analysis, max transition and max capacitance analysis. These two things are called as STA. So to understand setup and hold analysis, you have to understand all these things. So next is you will do routing, and we'll do all the checks after routing. Next we'll do sign off checks. Then if any changes are required, again we have to communicate to the physical design team, and they have to make these changes. That is called as ECO, engineering change order. ECO means what are all the changes your sign off team are telling, that changes you have to do in your design to solve the violations. That is called as ECO. If any ECO is there, we have to implement that ECO. Then the block we have to send for full chip level designer. He will integrate the blocks, he will create GDS2 file, and then we'll send to foundry for fabrication. So this is a process involved in physical design. Right? So now prerequisite, right? There is some prerequisite for this. What are prerequisites? So you should be knowing Unix, because we use this tool, IGC2 tool, in Linux operating system. So you should be knowing how to use Linux operating system by using Unix commands. So you should be knowing Unix commands, how to create a folder, how to move from one folder to another folder. So how to grep any word in a file, right? How to delete a file, how to copy a file, how to move a file. All these things you should be knowing by using Unix commands. Unix commands you should be knowing. Next, main important thing, you should be knowing CMOS basics. I think you already know about this. You already undergone this training. What is inverter? How to build a NAND gate by using CMOS technique. How to create NOR gate by using CMOS technique. What is fabrication steps? And what is layout? And how to draw the layout for inverter, NAND gate, NOR gate. You should be having the idea. This much you should be knowing for CMOS, CMOS basics. So after this, you should be knowing TCL. Right? TCL is very, very important, because to solve these violations, so you should be knowing TCL, tool command language, because ICC2 or any of these tools can understand only TCL, tool command language. We can communicate to the tool by using graphical user interface that is there, but we have to communicate through command, means we should give only through TCL. So we can use TCL to make automation also, because we have all these violations. If we want to fix these violations, for example, I'll get 1000 violations. If I want to fix these 1000 violations, if I do one by one, I have to do the same step 1000 times, which is very irritating, right? Instead of that, I can write the automation script. Automation script I can write, and just to source that file, right, your tool will fix everything by reading this automation file. So for that reason, you have to understand what is TCL, right? So this is a prerequisite. So here how the course starts, right? How the course is. Here we have two classes. One is theory, right? Only on weekends. Weekend means Saturday and Sunday. We have theory. Theory is done only on Saturday and Sunday. And lab, we have lab. Lab means we will use tool and we will start doing the projects. Right? Here projects are done. So lab is again two types. So one is weekdays lab and another one is weekend lab. So weekdays lab will run from Monday to Thursday. It is from Monday to Thursday. Sometimes they will modify, because if the mentor is on leave, they may give, for example, mentor is applying leave on Tuesday. So they will give leave on Tuesday and they'll conduct on Friday. Only few cases. Not every time, few cases. But general timings is from Monday to Thursday. Right? So weekend lab, weekend theory for every student, weekend theory is on Saturday and Sunday. But only lab, right? So those who cannot attend weekdays lab, because few will be working. Right? Those who are not able to attend weekdays lab, they have weekend lab. So this weekend lab is on only Saturday and Sunday after the theory classes. Theory will be in the morning. After theory classes, we will be having lab Saturday and Sunday. These two labs are separate. So weekday students should not attend weekend. Weekend should not attend weekdays. Right? Weekend lab is special lab only for the students who are not able to attend on weekdays. few will be working, right? They cannot attend. So we have Saturday and Sunday separate lab, weekend lab. So this advanced course will run for 3 to 4 months, in between 3 to 4 months. So like it may take 3.5 months, right? It depends upon the holidays, how much holidays we get in between. We get, see, for example, we have now the Dasara, we have Deepavali, we have. If we have holidays, it may extend like 3.5 months or 3 months, 20 days, like that. Max to max 4 months. Minimum 3 months, max to max 4 months, not more than that. So minimum is 3 months. Minimum we want 3 months. So for that reason, I mentioned it will take 3 to 4 months. So in this 3 to 4 months, what we do is we'll understand the different concepts in physical design, and we will do one lab. This complete lab. For one project, we'll do all the steps from input files to the sign off checks. We'll do from one project. We'll also write many TCL scripts. Right, advanced TCL scripts we'll write. So basic TCL scripts we already written for prime numbers, right? For factorial of a number, doing some small file operations you have done. So advanced TCL scripts will write in one project flow. One project flow you will do with help of mentor. Another project we will give to you people that you should do. So totally we'll give 2 projects. If any doubts you have, you can ask me. So role of PD is to convert gate level netlist to this physical form. This is role of PD. So these are all layouts, right? Layouts of macros, layouts of standard cells, and connection is done through metal layer. So this is the role of physical design in a short form. Now you can ask me if you have any doubts. I think this is already done in your basics weather design, ASIC design flow. The students who have attended basics, this is already done, right? Yes, whether it's already done, this one, ASIC design
Yes,
flow,
sir.
what I told now. Yes, it's already done. It's our responsibility to do once again in the demo class, is advanced physical design demo. Right, to give you what is, so the 3 things what I told, right, I have covered in demo, right? Why physical design, what we do in physical design, right? So what is the course details, how that course runs, right? I have given the information. Any doubts you have, you can discuss. Yes, any doubts you have?
So, sir,
Yes, tell me.
for weekdays, students also having theory questions on weekend only, no, sir?
The theory is for both. This theory, right? It is for weekdays and weekend both. Lab is only different.
Okay.
Weekdays lab is different. Weekend lab is different. This weekend lab is specially done because those who cannot attend weekdays lab, only for them we have weekend lab.
Okay, sir.
See, tool access is for 24 hours. Right? They will give you the VPN. You can access 24 hours tool. See, but we see there is again 2 things, right? You have your lab days, right? You will be having lab. In lab hours, Like for example, you have lab from 9 to 1. You have lab. So you can access the lab tool within this hours 9 to 1. So we request the students not to use between 2 to 5 because other batches will be going on. We want license for them. So 2 to 5 we request. It is not that you cannot use. We will not block it. Right? We request not to use because other batch will be going on. They see similarly when your batch is going on, we will request other students not to use in this time because the students who are doing the lab, right, attending the lab classes, they want the license. So 2 to 5 we will ask you to not to use. It's a request. It's not that we are going to block it. After 5 o'clock, you can use it at any time. That's your wish. Because all this we want a license. License is very costly. License is like it is in lakhs, right? For 1 year we have to pay in lakhs, more than 10 lakhs to get the licenses.
Sir, is there any
So,
changes in timings for a theory and lab?
yes, the timings will be changed for sure. It depends upon the convenient when the mentor is available. If we are already having 1 or 2 batches already running, right? The batches are already running, so we cannot put 2 batches at a time because we want license. 2 batches I cannot do in the morning only. It's not that mentors are not available. We have enough mentors, but we don't have that much license to handle 2 batches at a time. So licenses are very costly. Right? For few licenses, you have to pay in lakhs. So industry will also not give you the license, tool license when you're on the training, right? Industry will give you the license only if you're working on the projects. They will not give you the license when you're on the training, right? In the training, they'll not give you any license. So for that reason, so timing will vary. Timing way may vary. That admin will inform you. It may be in the afternoon or it may be in the morning, right? It is like the weekdays batch. It is like they will see that it will not overlap on with other batches. That is a genuine problem. It's not like intentionally we are doing because the reason is both the batches should get the license, enough license. None of the students should be left out without doing the lab. So weekend theory classes, it depends upon the available of trainer. A few trainers like they will be having, for example, if you have industrial trainers, right? Some trainers they will be going to work on Saturday morning. They will be available only after afternoon. Right? At that cases, we may have only theory in the afternoon. In special cases, not every time. So timings also vary based on the trainers.
Okay, sir.
Yeah, hello, sir.
Yes, tell me.
Yeah, what are the tools we need to install, sir, for
That admin will give
IC2?
you. See, they will give the information. They will take the class for tool installation. I think they'll start from
Okay.
Monday or from the next week. Admin will inform you about that. They will take the classes for tool installation. They will do it. And mentors are there. They will guide you how to open IGC2 and done. Okay. That is part of course. Installing the software, opening ICC2, right? That is part of course. That is part of syllabus. We will take care about that during lab. In the group, admin will inform you at what time they will start.
Sir, like I have heard that verification and DFT are the booming. Like already PD engineers are more than enough. Like it will affect us.
See, it depends. I cannot tell anything about that now. Now, I will be very frank, it is slow. The placement of PD engineers is slow. Right? I'll be true with that. Now it is very slow. It may improve, right? Because if the course needs 3 to 4 months to complete. After that, it may improve. But now, see, there is few candidates who are on the bench. They should be handed to the projects. They should go to the projects. Right. After that, there will be new recruitment happens.
Okay, sir.
See, the reasons why other domains has more job opportunities less than physical design means last year they have done a enormous recruitment for physical design, huge recruitment they have done. For that reason, see, when they have done huge recruitment last year, so obviously this year they want less candidates because they want to get the projects, right? The students who are already recruited, they want to get the projects. Other domains, it was not like that. Other domains, the huge enormous recruitment was not happening in another domain, but it happened in physical design. So it is not like the other domains are booming and physical design is not booming. It's not like that. The reason is they have done huge recruitment last year. So for that reason, those students are on the bench, few students. They want to get the job. So for that reason, now there is placement is very slow. Other domains, they didn't do like that. They were not having enough huge recruitment for other domains previous year. So now they are having the moderate openings, which is every as usual they have openings, right? The same openings is there for other domains. For physical design, for that reason, we have affected the placement now.
Okay, sir.
So, in PD, we use the ICC tool only now, sir. Then what OS and Fusion Compiler tools, sir. How can we use it?
See, we use ICC too. Fusion compiler is nothing but it is a tool along with the sign off tools. Right? The sign off tools you can use ICC too. Both are same. Both commands are same. Fusion compiler is nothing but in the same tool you can use these three softwares. I think prime time is not available. This you can use. This you can use in ICC 2 only. That is called as Fusion compiler. That they have given the new name. Right? That's it. That is the difference. Fusion compiler.
Okay, sir.
Right? But in here we are using separate license. ICC2 is separate license. These are separate license. In Fusion compiler only you will get all these three softwares. The sign out softwares. That is called as Fusion compiler. But methods and commands are same. Both are same.
Sir,
Yes, tell me.
are you going to take the theory class for us for a PD?
Can I ask why this question is?
No, sir. Actually, PD demo is taken. That's why we are asking.
No, whether you want me to take or not to take.
Not like that, sir. Just asking. Don't know.
No, it's not like that. So we have to discuss and we will let you know who is going to take.
Okay, sir. Thank you.
So probably I may take or may not take. So the chances of taking me is more. Right? I will take it, but we'll discuss still. Right? We have to discuss about this. And we'll tell.
Okay, sir.
Sir, will there be a class tomorrow?
No, probably I think. Tomorrow there will be no classes. From weekdays they may start the classes. That admin will inform you.
Okay, sir.
So 95% there is no class tomorrow. Because see, this demo is done even for the students who are directly joining for demo. Right? Few students will directly join for advanced courses. So even we will give this time for students to enroll. You people have already undergone to the basics, right? Few will directly join to the demo. So we will give some time for them to enroll. So tomorrow there is no class. So from weekdays, I think the classes may start. So that admin will inform you when the classes starts. Yes, then thank you. Thank you.
Thank you, sir.